lexicographers can inform you about time. The term time is the most frequently used noun in the English language. We can't go a day without discussing this concept. It makes you wonder how we denote time when we actually talk about it. If you say, "Meet me at 7 p.m., no one gets tense. There is no dramatic reaction to these abstract ideas. As for 7 p.m., we all understand what needs to be done practically. Time, in a sense, serves only as a label for individual phenomena in the universe. The universe repeats itself at various moments in time that we define as such, and time helps distinguish one moment from another. So defining what time is not a problem, isn't it? The real puzzles arise when we talk about the properties of time. We possess past, present, and future. But how are they different from each other? We remember the past, but the future remains unremembered. Why is that so? Why do we all start life young and inevitably grow old? Why do we think we can influence the future but not the past? Is it possible to travel back in time? There are many perplexing questions regarding the nature of time, and many of them remain unanswered. However, defining what time is does not fall into the category of unanswered questions. One of the most conspicuous aspects of time is its inherent direction. Indeed, there's a distinction between past and the future. We often view the past as something that has already transpired, recorded in history, while the future remains uncertain and yet to unfold. The present is where we currently reside. However, when we delve into the realm of physics, we encounter a fascinating observation. Our most advanced theories in physics don't differentiate between the past and the future. This contrasts starkly with our everyday experience, where this differentiation is fundamental. To accept this idea, it takes some mental effort to entertain the notion that time might exist without a specific direction, much like how there's no intrinsic direction in space, yet space still exists. In our familiar three-dimensional world, there are such dimensions as up, down, left, right, forward, and backward. At the fundamental level of the laws of physics, there is no particular direction in space. Imagine yourself as an astronaut floating in a spacesuit. There is no way to distinguish one direction from another. No physical experiment can determine a particular direction in the universe, but space certainly exists. Conversely, time would remain a part of existence even if it had no definite direction or arrow. However, here on Earth, we observe the directionality of space. For example, if you pick up a cup of coffee and let it go, it will invariably fall downward. This distinction between up and down is obvious, but no one suggests that it is a fundamental aspect of the universe. It exists because it is inherent in the laws of physics. The reason we perceive an arrow of time in our everyday lives is similar to how we perceive the distinction between up and down on Earth. We are in the aftermath of a significant event, the Big Bang. This concept leads us to the notion of entropy, which describes the level of disorder, randomness, and messiness within a system. When things are orderly and organized, they exhibit low entropy, whereas when they are chaotic and disorganized, they have high entropy. In the universe, there's a natural tendency for systems to transition from low entropy to high entropy, a principle known as the second law of thermodynamics. The profound question, however, is why the universe started with low entropy in the first place. The question of why the world had less entropy yesterday than it does today is indeed perplexing. The explanation often given may not be entirely satisfactory in itself. Essentially, it boils down to the fact that entropy was lower yesterday, because entropy was even lower the day before yesterday, and so on, tracing this chain of reasoning back 14 billion years to the Big Bang that marked the emergence of our observable universe. The universe began in a hot, dense, and extremely low entropy state, and has been steadily increasing its entropy ever since. In the field of philosophy of physics, this concept is called the past hypothesis, a term introduced by philosopher David Albert. Essentially, if one understands that the universe is made up of atoms, understands the concept of entropy in relation to the reorganization of these atoms, and accepts the past hypothesis, according to which the entropy of the universe started from an exceptionally low level, then all subsequent events can be explained. There is an erroneous view of human life and entropy. The view that life, that is, living things, biological organisms, that consume food and everything else, is a struggle against increasing entropy. In fact, life owes its existence to the fact that entropy is increasing. After all, if entropy were not increasing, it would mean that nothing significant was happening. There would be no interesting events, no memories of the past, and no causal influence on the future. In the absence of entropy growth, the universe would be in a state we call thermal equilibrium, where everything is homogeneous and unchanging. It would be the most calm and monotonous state imaginable. Instead, as part of the scientific quest, we need to find out why complex and intricate structures arise at all. Obviously, they require increasing disorder as they age to maintain their existence. We've already reached the maximum level of complexity. It does not follow that they must necessarily appear. Consider a famous example. Imagine a small bottle of perfume in a large room. When you open it, the perfume disperses into the room, increasing entropy. However, when you think about it, when the perfume is in the bottle, it is quite simple. Likewise, once spread around the room, it remains relatively simple. It has traveled from a low entropy state to a high entropy state, yet it remains uncomplicated. It is the journey from an initial state of low entropy simplicity to a final state of high entropy simplicity that opens up a wide range of possibilities where things can be complex. The distribution of perfume may vary from room to room. Swirls may be caused by air currents in the room and other factors. The universe works on a similar principle. Initially, our universe was uncomplicated and had low entropy. However, over time, stars fade away, black holes vaporize, and the universe becomes dark, empty, and becomes uncomplicated again, but with high entropy. It is at this intermediate stage that complex, entangled systems like us can and do arise, living off the increasing entropy of the universe. This whole story is still not fully understood, and it remains an interesting and active area of scientific research. Why did complex structures such as living organisms arise the way they did? What role does information play? What chemical and geological processes are involved? Could similar events occur on other planets? These are intriguing questions. One thing we can be sure of, however, is that without the constant increase in entropy, none of these phenomena would be possible.